Today, Greg and I will be giving a brief presentation on the uses and history of piezoelectrics. Now, what are piezoelectrics? Piezoelectrics are a material that when subjected to a pressure create an electric charge, and an inverse pressure or tension creates an inverse charge. They have a high modulus of elasticity compared to many metals, and they can also be used in very high temperatures, with tests finding that the material will react the same up to the melting point. Now, for brief history, the word piezo is derived from the Greek word for pressure. The piezoelectric effect was discovered by Jacques and Pierre Curie in 1880. They found that the pressure applied to a quartz crystal creates an electric charge in the crystal, a phenomenon they referred to as the direct piezoelectric effect. Later, they also verified that an electric field applied to the crystal leads to a deformation of the material, the inverse piezoelectric effect. In the subsequent century, research has been performed into the development of materials with improved piezoelectric properties, enabling commercial utilization of the piezoelectric phenomenon. Some modern uses of piezoelectrics vary greatly. An important use of them during the 20th century and during World War I was sonar. The first piezoelectric was used in submarines and in their sonar to help detect what was around them. Piezoelectrics can be sensitive enough that they detect the pressure difference created by a strong sound wave. Piezoelectrics are also used in airbag sensors. They help monitor combustions in the manufacturing process of combustion engines, and even the collagen in the bone is a piezoelectric, believed to act as a biological force sensor. To date, the number of applications of piezoelectric materials are still increasing.
Now on to the structure of piezoelectric materials. The piezoelectric effect is exhibited by 20 out of 30 crystal classes and is always associated with non-centrosymmetric crystals. This occurs naturally in materials such as quartz, which happens to be more stable and has more consistent properties over wider temperature ranges than that of the typical lead zirconate titanate, which will be discussed later. A typical non-centrosymmetric crystal structure, such as perovskite, in this case we use calcium titanate, has a net non-zero charge in each unit cell of the crystal. However, as a result of the titanium ion sitting slightly off-center inside the unit cell, an electrical polarity develops, thereby turning the unit cell effectively into an electric dipole. A mechanical stress on the crystal further shifts the position of the titanium ion, thus changing the polarization strength of the crystal. This is the source of the direct effect. When the crystal is subjected to an electric field, it also results in a relative shift in the position of the titanium ion, leading to the distortion of the unit cell and making it more or less tetragonal. This is the source of the inverse effect. On to the most manufactured piezos. In this case, the most manufactured piezo is lead zirconate titanate, also known as PZT, which is considered to be the most effective and economical to produce to date. However, it is also considered to be very unsustainable and toxic due to its lead base. And it is both a piezoelectric and a pyroelectric, meaning that it develops a voltage difference across its faces when not only experiencing mechanical stress, but also when experiencing a temperature change. So then it is the material of choice for making ultrasound transducers for speakers and microphones as well as other sensors and actuators. And being the most economical to produce, the image here with the ceramic PZT discs are an example from a Chinese manufacturer that produces them for about 50 cents a piece at a minimum order of around 1,000 units. On to Oregon's research in sustainable alternatives. At Oregon State University, the Material Science Department has been doing research on piezos for a number of years now. Specifically, research has been led by Dr. Brady Gibbons on lead-free alternatives to the popular PZT thin films. Using a barium base, promising results have been found in the form of bulk films. However, these production techniques need to be developed further for the use in thin films. The second image here is a view from inside Dr. Brady's custom-designed sputter system. The sputter system is used to apply platinum electrodes to the face of the thin films to be tested for electrical properties. To put it briefly, sputtering is a plasma-based deposition process in which energetic ions are accelerated towards a target. The ions strike the target and atoms are ejected, or sputtered, from the surface. These atoms travel towards the substrate and incorporate into a growing film. In this sputter system's case, argon ions are energized to strike a platinum plate and are ejected onto a holstered thin film. A grate is then placed over these thin films to create the electrode pattern on the surface. And for their next-gen uses, per se, piezoelectrics are still being studied for a greater role in tomorrow's world. For instance, the application of piezoelectrics in biomedical science is a very exciting frontier in material science. The idea is that piezoelectric transducers can be implanted into the body to give greater in-depth monitoring into one's health. Another potential benefit to implanted piezoelectrics is the potential to be self-powered and flexible thin films. The image here is of an experimental ultra-flexible piezoelectric device integrated with a heart to harvest biomechanical energy, and this was done by the Chinese researchers at Tsinghua University. However, issues such as size limitations, biological compatibility, and flexibility have led to investigation into polymer, composite, nanostructured, and lead-free piezoelectric materials. As we said previously, piezoelectric materials do form naturally in the world, so one way to develop biomedical devices is to look at the naturally occurring piezoelectric structures within the body and see how they can be developed to create a piezoelectric medical technology compatible with the body.
Thank you for listening to our presentation on piezoelectrics, and we hope you learned some cool things.